Today the plan for the lecture and the seminar would be as follows. First of all, I'm going to give a more detailed explanation about midterm test, because I have sent you the solutions to the problems, but probably you might wonder why these problems were actually chosen for the test, and I would give somewhat extended explanation. I will try to show different ways to solve these problems. And then on the second part, we are going to have a lecture about the basics of probability theory and statistics. So I'm going to roughly explain something about probability, because I'm not going to do this in a mathematically rigorous way. I'm going to do this in such a way that you can apply this knowledge to solution of the problems in molecular physics. Because starting from this lecture and seminar, we are going to proceed with the second part of our course, which is related to the molecular physics. Molecular physics. And the main difference of the second part of the course from the first one is that starting from this lecture, we are not going to ignore the molecular structure of matter. So we are going to study the random chaotic motion of a huge amount of molecules, and we'll try to figure out how this motion results in the thermodynamic laws that we have established during the first part of the course. So let's first start with the midterm test. And I don't have marks for today, so I'm going to send your marks individually to everyone with my comments on your midterm test. But I'm going to give a rough impression of me about your midterm test. So I have mixed feelings about your test, and part of me is actually happy that you were able to grasp to some extent the possible methods which can solve these problems. The other part of me is slightly unhappy because mostly, even if you were able to correctly identify the method to solve a problem, often it turned out that you make some mistakes which prevent you from obtaining the correct answer. So even if you have chosen the correct method, then on the way to the answer, you do something, or you misunderstand something, or you do some mistake, then the answer is actually wrong. At the same time, mostly as I see, the mistakes you've been doing in your problems are different, so that means that you were pretty honest in solving the problems. So almost no cheating was involved in the test. So I think that's also good news. And probably I will adjust slightly the evaluation criteria for the midterm test in order to somewhat reward people who were trying honestly to solve the problems, but were somewhat unsuccessful on the way to the answer. Okay, so now let's start with the first problem. I have sent you the solutions which were quite not optimal, because I was producing these solutions on the way to the classroom, and partly I was testing the amount of time which is required for me to solve all these problems. So I had roughly about half an hour to solve all of them, because it's about the amount of time I spend in train without interruption. So I have crossings on the way from home to here, but so that limits the amount of time. So I sometimes choose not the optimal method, but I just try to understand whether it's possible to solve these problems in the limited amount of time. You haven't received the solutions so far. Let me check. Sagar, okay. Well, I'm going to do this during the break and see if I have everyone in my mailing list where I have sent the solutions. Okay, please tell everyone else here whether you have obtained received solutions or not. I didn't receive. Okay. Okay, so probably something went wrong, and instead of solutions, well, they haven't. Okay, so actually I was pretty sure that I have sent an email on the very same day that we had the midterm test. So in the evening after the midterm test, probably somewhere close to the night, to the midnight, I was trying to send solutions. Okay, let me check it now, because that's interesting in all ways. Now I understand what has happened actually, because I was, yeah. Now I think the solutions should be right here, because I have composed an email, and after that, well, it remained in a draft version, so it didn't. I haven't actually clicked the button of sending the email, so forgive me for this. That's bad, really. I was pretty sure that I have done this. So, well, now let's start with the first problem. It was formulated as follows: that we have a process. So then you can compare these solutions with the solutions that you should now have on your email and see the difference. So we have a process which is described by the linear equation P equals to B minus AV, where P is the pressure, V is the volume, and we need to determine the heat capacity of the gas in this process as a function of volume. So as a function of volume. And we know that we have an ideal gas, and so we know the molar heat capacity at constant and volume and constant pressure. So now we have a pretty standard problem, but nevertheless the problem is quite interesting. So because I have minus here leads to the following dependence. So if A is positive, then the dependence of pressure as a function of volume should look like this. At zero volume it should be B, so it should also be the volume of B over A when the pressure reaches zero. Of course, we cannot exactly reach these points, so I think the process should have something like some kind of like this appearance. Okay, so now for the determination of the heat capacity. So the heat capacity is, so by definition, I can do this different ways. So one of the definitions, this is the temperature multiplied by ds over dt, because actually this is delta Q over T. So I have T times ds over dt, and in the solution that I have sent you by an email, I have used the equation for entropy to solve this. So I have written the entropy of the ideal gas as follows, that this is Cv logarithm T plus R logarithm V. So that means that I can write that ds is Cv dt over T plus R dV over V, and then continue until I get the answer. Now I'm going to use, instead of this formula, I'm going to show you the way to solve this problem without resorting to entropy. So I'm not going to use the equation for entropy. I'm going to use the definition of the heat capacity as delta Q over dt, and by the first law of thermodynamics, I need to write du plus pdv over dt. And in the case of ideal gas, I know that du is actually Cv dt. So the internal energy is independent of volume. So that's what I'm going to use here to write this. Instead of du, I have written Cv dt. So no changes in the internal energy which are associated with the change of the volume. So this is valid for the ideal gas, and now I continue, and I see that these dt and dt can cancel out, so I can write that this is Cv plus P times dV over dt. So what now I'm going to determine is the derivative of dV over dt. To determine this derivative, I need to write down the, so I'm going somehow like, what is this? So in order to find the derivative dV over dt, I need to use the equation of state. So I assume that I have 1 mole of gas, so I can write that PV equals to RT. And now I can write it like this, that d PV equals to R dt. And now I can expand this expression as follows, that this is V times dP plus P times dV equals to R dt. And to obtain the answer, I need to take into account that according to this equation, if I differentiate both sides of this equation, I can write that this is dP equals to minus A dV. So now I'm going to insert this instead of this dP and get that minus A V dV plus P dV equals to R dt. So now I have a perfect linear equation for dV as a function of dt. So I can get from here that dV over dt is R over something like P minus AV. So if I substitute instead of P that this is B minus AV, so I can write that this is R over P minus 2AV. Okay. Good, so now I can plug this into this equation and get that this is CV plus pressure over, oh, it's not, this is B minus 2AV. Oh, well, I can do it like this, P over P minus AV times R. And why I'm doing this, because I want to somewhat simplify the expression, so I want to do like follows. That this is CV plus, and in the numerator I can write that this is P minus AV plus AV over P minus AV R. So we can see that if I divide P minus AV by P minus AV, I get 1. So that would be CV plus R plus AV over P minus AV. And I understand that P minus AV is B minus 2AV times R. And CV plus R is actually, by Meyer's relation, you know that CV plus R should be CP, molar heat capacity at the constant pressure. So now this is the final answer to this problem. And, well, actually, with this we can conclude the solution. Yeah? But now goes some analysis, because I just don't want to stop the solution of the problem at this point. So what I'm going to do now is to analyze this expression. So I want to see how this Cp plus AV over B minus 2AVR actually changes as a function of volume. C equals Cp plus AV over B minus 2AV R. Well, I can immediately see that this equation is not determined at all of the volumes. Because if I have B minus 2AV equal to 0, then something wrong happens, because I have division by 0. This is at V equal to B over 2A. V equals to B over 2A. So let's again plot the dependence of pressure as a function of volume. So I have B, so I have B over A. So now, yes? Huh? Comment. We can see the final part of the answer. In here. Yeah? Okay, let me write this once again. The final answer is C equal to Cp plus AV over B minus 2AV multiplied by R. And now I'm exactly analyzing this expression. I have rewritten it here. So that's the final answer. And now I'm attempting to analyze this. And what I get here, that's that there is this particular volume of B over 2A, which is coincidentally half of the maximum volume B over A, at which something interesting happens. Actually, we have division by 0, so that means that formally the heat capacity approaches infinity. So as I go closer and closer to this point, then my heat capacity becomes infinite. So let's remember what infinite heat capacity means. So let's write it once again. That is C is delta Q over dt. So essentially, to make the heat capacity infinite, you need to do either of two things. You need to either make this delta Q infinite, but that can't happen actually. Or we can make it by making dt approaching 0. So this point at which volume equals to B over 2A, we have dt approximately equal to 0. So that means that at this point, this curve is tangent to the isotherm. Because if I have a linear dependence which is tangent to the isotherm, so at this particular point, if I slightly change the volume, that actually means that there is no change in temperature. So that means that small part of this linear curve is the part of the isotherm. So this is the point where I have tangent to the isotherm. And indeed, how can we describe the tangent to the isotherm? That we need that dPV equals to 0. Yeah, so that in order to have the part of the isotherm, I need to have dPV equal to 0. So I can write that's like follows, that dP VdP plus PdV equals to 0. Then I remember that dP equals to minus AdV, so I can write that minus AV plus PdV equals to 0. So that essentially means that at this point P equals to AV. So if I plot the curve P equals AV starting from the origin, so that would be a cross-section point. And since the angle between this curve and x-axis is the same as the angle between this curve and again x-axis, as you see, so we have an equilateral triangle here. So that means that indeed the cross-section point of these two lines should be a line above the middle point of this line from 0 to B over A. So now I think that explains why we have this, that at V equal to B over 2A we have infinite heat capacitance. So now let's continue with the analysis of this equation. There is another interesting part of it. Not only it can be infinite, it can be 0 and it can be negative. So it can also change sign. So starting from positive, it can become negative or vice versa. So let's see. So let's write it. So that would be a Cp times B minus Cp times 2AV plus AVR divided by B minus AV. I have written this as a single fraction, in a single fraction form. That allows me to understand, well, how the sign of this expression changes as I change the volume. Well, as you see here, if I take, for example, if I take volume equal to 0 or approaching 0, if I take a very small volume, so these two can be eliminated. So I would have C above 0. Okay, so now if I take a very large volume, then I think the first term can be neglected. So if volume goes to infinity, well, it actually cannot happen because we have this kind of limit imposed by this. But nonetheless, as I increase the volume, I have the negative contribution and positive contribution. And I know that Cp is equal to Cv plus R. And Cv should be positive, so that means that this is greater than R. So that means that this second term, negative term, is larger than the third term. So as I increase the volume, my heat capacity, so the numerator would decrease. So as volume increases, the numerator, so Cpb minus Cp times 2AV plus AVR decreases. So it makes natural to find, so if this quantity decreases, that at some point it should reach 0. So that determines the volume at which this becomes 0. So we need to solve the equation Cp times B minus 2 Cp AV plus AVR equal to 0. Well, it's actually a very simple equation. I can get all of my terms which contain V to the right-hand side. So now I get that this is Cp times B over 2 Cpa, 2 ACP minus AR. Okay, so what can be also done with this? So I can take A as the common, So I get that this is B over A times Cp over R over 2 Cp over R minus 1. Like this. So let's change, for example, Cv and see how this volume depends on the composition of the gas. So if I have a single atomic gas, then Cv is 3 over 2R and Cp is 5 over 2R. So Cp over R is 5 over 2, so I can get that V for a single atomic gas would be B over A times 5 over 2 over 10 over 2 minus 1, so over 4. So I get 5 over 8 times B over A, 5 over 8. So if I go back to the dependence of pressure as a function of volume, I can plot this 5 over 8 R over, or B over A. Since 5 over 8 is larger than 4 over 8, so that means that this point is actually located to the slightly farther away from the tangent to the ith term. So what's the meaning of this point? So at this point, the heat capacity is 0. So essentially that means that at this point, delta Q is 0. So actually that means that this point is the tangent to the adiabatic curve. So where you have the tangent to the adiabatic curve, you would have the heat capacity equal to 0. So that should be that is what should be expected. Okay, so now let's look once again. In here I have positive heat capacitance. Then I go here and here and here. Okay, I have here B minus 2AV. What actually happens? B minus 2AV. So, okay, if the volume is very small, then I have a positive. Here I approach the infinite heat capacitance, and then heat capacitance becomes negative. That happens because, not because I have stopped supplying actually the heat to the gas. It happens because delta Q is greater than 0, but dt is negative. Dt here is negative. So in here I have reached the maximum temperature. In here the temperature decreases, but delta Q remains positive, so overall heat capacity is negative. Now it once again changes the sign as delta Q becomes negative, while delta dt also remains negative, and once again I have positive heat capacitance. So now let me plot all of this. As a function of volume. So C as a function of volume has the following dependence. So here I have this point B over A, which gives me the maximum possible volume in my problem. Here goes B over 2A. So it goes like this. So we start from somewhere, and here we reach the infinity. Then we continue going from here. Then I'm crossing here 0, and then I have some positive heat capacity. So probably this is not up to scale, but this represents some kind of a tentative dependence of heat capacity as the function of volume. Okay, so now let's plot delta Q, for example, over dV as a function of volume. Why do I plot this actually, delta Q over dV? The reason is that this is important in order to understand at which part of your curve a gas actually acquires heat and at which part of the process the gas loses heat. So in here, as I have said, that I have this B over A, I have this point 5 over 8 B over A. So if I plot this, well, again, not up to scale, so probably it would be somehow positive when my volume is below that 5 over 8, and it's negative when the volume is above 5 over 8 B over A. So here I have positive, negative. So actually, that's very important. So, because in one line of your curve, you can have a part of the process in which you have positive amount of heat supplied to the gas, and another part of the single line would have you negative amount of heat supplied to the gas. So this problem is actually intimately connected to the problem set which I have sent you for the preparation for the exam, in which I had this kind of a process. So in here, from the previous year. So in here I have adiabatic process, and in here I had linear process. So if you assume, for example, if you assume, and it was required to calculate the heat efficiency of the engine which operates in this process. If you simply assume that at this part of the process you acquire some heat, if you neglect that at only part of this process you acquire heat and another part you lose heat, so that would give you that actually the amount of heat in the process 1, 2, according to the first law of thermodynamics, should be equal to the change of internal energy plus work done, delta U1, 2. At the same time, the amount of heat in the process to 1, which is adiabatic process, is obviously 0. So that means that overall, the total work done should be equal to the amount of heat at the process 1, 2. So that would formally give you 100% of efficiency of this heat engine. But of course, it's wrong, because you need to divide this process into two parts, in which Q13 is positive and Q32 is negative. And this point which divides this line into these two parts is actually the tangent to the adiabatic. And as you see, I can plot series of adiabatic curves, and as I go from point 1 to the point 3, I get from this adiabatic curve to the upper and upper adiabatic curves. And when I go from 3 to 2, I go backwards on adiabatic curves. So that means that entropy increases here and decreases from here to here. Okay, so I think I have given a very exhaustive explanation about the problem number 1. So I can continue with the other problems. Any questions about this one? No, I don't see any. So if you have, please write in chat, and we can discuss these questions further. Okay, the problem number 2 was formulated very difficultly. So it says that if we consider some model for atoms which carry magnetic moments, then the entropy for these atoms, for the chain of atoms which carry magnetic moments, is given by the following expression: n-1 logarithm of 1 plus e to the minus 2 beta g, where beta is a reciprocal temperature. These expressions typically arise in the statistical physics. So if you consider some microscopic system, then you can, for the microscopic system, you can calculate the entropy. If you understand how interaction between different parts of this microscopic system is governed. So if you understand the laws of interaction, you can write the entropy. But in here, this part of the derivation for this entropy was carefully omitted for you. And what you need to do is you need to calculate the heat capacity of this chain, and that actually goes like this. Temperature times the derivative of the entropy over the temperature. So I can replace this beta by 1 over T. And I just need to calculate the derivative and multiply by T. So nothing difficult. It's just the calculation of the derivative. So, and I believe you all understand how to calculate the derivative. So in this derivative, the first term is the constant, so it can be omitted. Its derivative is 0. Then I have a logarithmic term. N minus 1 is constant, so I have this common factor. And when I calculate the derivative of this logarithm, I need to carefully apply the chain rule for calculation of derivative. A logarithm of something gives you as a derivative 1 over the expression inside the logarithm. Then I multiply it by the derivative of this expression in the denominator. So I have exponent of something. So when I calculate the derivative of the exponent, of course, that gives me the exponent. And finally, I need to multiply this by the derivative of the term in the exponent. So that would give me 2g over t squared. Okay, so now I have t and 1 over t squared, so I can eliminate this t. And that's actually, that's the answer, almost. I just slightly simplify it. I noticed that I have exponent here and exponent here, so it occurred to me that I can actually divide the numerator and denominator by this exponent, and finally get that this is 1n minus 1 times 2g over temperature, and divided by 1 plus exponent of 2g over t. So that's the end. Okay. This was considered one of the simplest problems for the whole test, so it takes about a few minutes to solve it if you understand what is required. So the requirements for the solution of this problem is the understanding of the definition of the heat capacity and its relationship to the entropy. And this relation has arisen on multiple problems which we have solved in the classroom and which were given as a homework. So I have considered that everyone should be able to solve the problem number 2. Okay, now the problem number 3. It's about the van der Waals gas, and when I talk about van der Waals gas, it's always somewhat more complicated than than when I have a problem about ideal gas. So I have a Joule-Thomson process, so in which the enthalpy is constant, and I have said that in this Joule-Thomson process, the final volume is much larger than the initial volume, so that in the final state, we have almost ideal gas. So I can assume that the volume is so large that all of these, that I can write that V minus B is approximately equal to V2, and also A over V2 is approximately equal to 0. That's, this assumption would help just to slightly simplify the algebra, otherwise the formulas would be larger. So the question of this was to determine the final temperature and the change in the increment of entropy in this process. So let's go and calculate it. For this, we need to have actually the enthalpy for the van der Waals gas. And the enthalpy is, by definition, internal energy plus PV. Okay, internal energy for the van der Waals gas is the standard formula which was derived during the lectures. This is CVT minus A over V. And for PV, I can use the equation of state for the van der Waals gas. I have also done this on multiple occasions during the classwork and during the seminars. So RT over V minus B minus A over V squared times V. So that gives me the final expression for the enthalpy in the form of CVT minus A over minus 2A over V. The coefficient 2 is due to this second term in the brackets, plus RTV over V minus B. Okay, so in the initial state, I just simply write this equation and insert T1 and V1 instead of T and V. But in the final state, I slightly simplify the expression, taking into account that V2 is much larger than V1. So I just remain here, leave here CV times T2 plus RT V2 over V2, because my V2 is so large that V2 minus B is approximately the same as V2, because B is so small compared to V2. So I can just divide this, or eliminate this V2. So I have just CV plus R times T2. CV plus R times T2 corresponds to the expression for the enthalpy for the ideal gas. So Cp times T2 gives you enthalpy for the ideal gas, and according to the Myers relation for the ideal gas, a molar heat capacity at constant pressure equals to Cv plus R. So that allows me to find the final temperature in a single step. Oops, some glitches happening here. So T2 is, well, I simply divide this one by this, so I can just slightly decorate the final expression in the following way, that I write it as T1 minus 2A over V1 plus BRT1 over V1 minus B divided by CV plus R divided by CV plus R. So that's the final answer for this part. And as I see, I have some mistake probably in my solution here. So, well, I have neglected this RT2. Okay, but nonetheless, so this is the correct answer here. And finally, we need to determine the increment in entropy. To do this, I need the expression for the entropy of the van der Waals gas. The equation for entropy goes as follows, that this is R times V2 minus B over V1 minus B. So here minus B can be neglected, plus CV times a logarithm of T2 over T1. So I just plug this expression for T2 into this and get the final answer. Delta S, that's actually a quite ugly expression. I want to say V2 over V1 minus B plus CV, a logarithm of 1 plus, or here actually, here goes or I can write this as plus. So 1 plus BRT1 over V1 minus B minus 2A over V1 over CV plus R at T1. That's the end. So that's actually was quite straightforward. Nonetheless, it requires you to know the expressions for the entropy and the internal energy of the van der Waals gas. Internal energy is this. Entropy is this. These expressions were derived during the lectures. So if you have them on your supplementary material, then the only mistakes in this problem you can do are actually the algebraic mistakes. So the solution is quite straightforward. The problem number 4 was surprisingly one of the most difficult problems for this midterm test, although I have designed this problem to be one of the most simple. I have even given a small hint in the text of the problem. I have said that in 1 degree Celsius, specific enthalpy of vaporization is given by some quantity. So that was 2.26 kilojoules per gram. So this is a specific enthalpy of vaporization. Not the typical name of latent heat of vaporization, but the specific enthalpy. In the problem, I wanted to underline the fact that actually this quantity is required to change the enthalpy of the system. So if you make 1 gram of water at 100 degrees Celsius change into, so 1 gram of water change into 1 gram of steam at the same temperature of 100 degrees Celsius. So this amount of heat you actually spent is a difference in enthalpy between these two different states of matter. Enthalpy. So this is the enthalpy of steam. So I have this steam at 100 degrees minus enthalpy of water at the same temperature of 100 degrees Celsius. So what you need to determine is the same quantity for 90 degrees of Celsius, which is at 90 degrees. And the problem is that you don't know the enthalpies at 90 degrees Celsius. But we were given also a heat capacity of water, which is 4.2 joule over gram. And okay, nothing was given about the heat capacity of steam, but it was said that steam can be assumed the ideal gas. Steam is ideal gas. So that actually means that first what you need to do in order to determine the heat capacity of steam, you need to first write the chemical formula of this gas. It's H2O. So that means that I have 3 atoms in one molecule. So I need to use the following equation for the molar heat capacity of 3 atomic gas. But since I want to study the changes in enthalpy, what I'm more interested in is not the molar heat capacity at constant volume, but the capacity at the constant pressure, which is Cv plus R, which is 4R. But these are molar quantities. So I need to have a quantity like specific heat capacity at constant pressure, Cp, which is equal to molar heat capacity. I don't know, it's actually not seen, but I try to make these molar quantities with slightly bigger letter C than specific heat capacity, and divided by the molar mass. So this is 4R over mu, and the calculations give that that should be something like 1.84 joules per gram. And as you see that specific heat at constant pressure of steam is lower than specific heat of water. So now I just can write that the enthalpy of water at 100 degrees minus enthalpy of water at 90 degrees equal to C water delta T. In the case of water in the liquid state, there is almost no difference for specific heat at constant pressure and constant volume. The reason is that, well, the volume of water doesn't change drastically, so that's why this difference between specific heat is negligible, and moreover, this quantity which is usually given, the specific heat, is measured in the normal conditions. So in the conditions when you have constant standard pressure applied to your water, so that means that actually this is heat capacity at constant pressure. That's why if I multiply by delta T, that would give me the change in enthalpy of water. And the same equation for steam is also Cp times delta T. So finally, if I derive enthalpies at 90 degrees Celsius from these two equations and plug them into this equation, I get that Q90 is equal to Q100 plus C water minus Cp specific heat of steam times delta T. So where delta T is 10 degrees Celsius. So from this I get the final answer of Q90 of approximately 2.286 kilojoule per gram. So there is a slight change of in this second digit after the floating point. So there is slight change, but what's important here is that Q at 90 degrees is larger at Q at 100 degrees Celsius, and that means that if I increase temperature, this Q value decreases. So the specific enthalpy of vaporization decreases. So if I plot this as a function of temperature, Q as a function of temperature, I would see this kind of a dependence. Not always this kind of a linear dependence, but at some point this specific enthalpy of vaporization would become 0. And as you should have guessed by this time, the specific heat of vaporization goes to 0 exactly at the critical temperature. So we have this critical state when the difference between liquid and gas form disappears completely, and of course in the state where there is no difference between liquid and gas form, the specific enthalpy of vaporization should be 0. So this is also one of the indicators that of the existence of the critical point, because as you increase the temperature, this specific heat of vaporization decreases. Okay, now the final problem, actually it was mechanics. I have seen that many people haven't started solving this problem, probably due to some deficiencies in knowledge in mechanics, because overall it's a very simple problem, because this system in which I have one plate moving at some velocity while the other plate is being at rest has been discussed during the lecture about viscosity. And I have said that the distribution of velocities goes like this. This is the distribution of velocities. And what is required here to understand is, okay, is the kinetic energy of the liquid. So how do we determine this kinetic energy? I need to integrate, since everywhere the velocity is different, I need to integrate this kinetic energy. So I start from, first I have some axis here, so this is 0, this should be d, the thickness or the separation between these two plates. Velocity as a function of h is given by the following equation, v times h over d. So it's 0 at h equal to 0, and it's v at h equal to d. So now I can determine the kinetic energy as follows. density, this is the mass per unit volume, multiplied by v squared over 2, multiplied by the element of volume, dH, and I have assumed that I need to determine the kinetic energy per unit of the surface area of the plates. So that means that I need to multiply by 1 in order to get the element of volume. Okay, it's a very simple integral. So this is rho times v squared over h squared over 2d squared times dh. Everything here except for h squared is constant. So I can get it out from this integral. Integration is carried from 0 to d. H squared, when integrated from 0 to d, would give us d cubed over 3. So overall, this is rho v squared over 6 multiplied by d. That's the kinetic energy. The second question is slightly more complicated. It says, find the amount of heat released in the system per unit of, again, per unit of surface area of the plate due to the viscosity. Viscosity is a friction, and as you know, the friction force causes you like heat release. And in here, in order to determine this amount of heat released per unit of time, we need to apply the following, that the amount of work done on the system, external work, is being done on the system, because in order to keep the upper plate moving at this constant speed, I need also to apply the force, F. So the amount of work done on the system is F multiplied by V, because per unit of time. So I need to, in order to find the work, I need to multiply force by the displacement. But if I want to find the work or power of my external power applied to the system, I need to multiply this by the displacement per unit of time. And displacement per unit of time is the velocity. And okay, I need nothing to divide it with, because all of this work done is released as heat, because there is no change in the mechanical energy of the system. We have a stationary flow. In the stationary flow, all velocities remain constant. The kinetic energy is constant. So that's why all of the work done on the system is transformed into heat. So this is F multiplied by V, and in order to determine the force F, I remember that I have the equation for the shear stress arising due to the viscosity. I need to multiply the viscosity coefficient by the gradient of the velocity. The gradient of the velocity is V over d. So this is actually eta times dv over dh. But since I have a linear dependence, then dv over dh equals to v over d. So if I plug it in here, that would give me eta times v squared over d. That's the answer for the second question. In terms of calculation, this is one of the most simple problems. So it requires you to understand, first of all, how to integrate in order to calculate the kinetic energy. And this is similar to one of the problems which was given to you as a part of the homework. The problem about the Poiseuille flow, but that was the flow in the tube. But in here, I consider even more simple, even simpler case. And the second part was quite tricky because it says the amount of heat, and you need to guess that this amount of heat needed to be calculated from the energy conservation law. Because there is no change in the mechanical energy, that's why all of the mechanical work done in the system goes into heat. And more importantly, this heat is released uniformly in the volume of the liquid. Because if you consider a thin slice of liquid, you would see that there is shear tension, shear stress here and here of the same amount but different directions in this. But since this part is moving slightly faster than the bottom part, that means that there is total amount of work done on this small portion of liquid. And that would give us tau times dV for the amount of work done per unit of volume of this liquid. Okay, for per unit of volume, that would give me dV over dH. So I need to divide this by a small dH, the thickness of this portion of water. So that means that heat is being released uniformly in the volume of the liquid, uniformly. Okay, that concludes the solution of the midterm test problems. And if you have any questions, please ask them. So mostly I have tried to make them simple, but there were some tricks inserted in this problem. Sometimes I wanted for you to guess these messages. For example, on the problem number 4, I have written a specific enthalpy of vaporization deliberately in order to hint you on the change of the enthalpy that you need to look for. So in here, there is an enthalpy change. And the problem number 5 is the problem about the fluid flow. We had 2 lectures devoted to this topic. This topic is slightly, I would say, on the sidelines of the thermodynamics, but nonetheless, it's a part of our course. And since we had 2 lectures spent on this, I felt like I need to include some problem about the fluid flow. Okay. If you have any opinions about my choice of the problems, you can write them to me. So, for example, like you were not prepared for this or that, or like you had expected some other types of problems. But nonetheless, that would be a very interesting feedback for me. And I will try to make a better choice of problems for the final test. Well, I wish you spend a bit more time preparing for the test and solving the homework problems. And most importantly, homework problems should be solved before the test. And one of the reasons for that is that by solving your homework, you prepare for the test. And if you don't have your homework ready by the time of the test, that means that the probability of your test going wrong is higher than when you have your homework done already. So now we are going to start the part of the lecture about the probability theory. Of course, I don't want to make a rigorous introduction into probability theory, which is the job of our mathematical department, but I just want to remind you of something if you have already studied the probability theory, or to give a gentle introduction into the subject if you haven't met this subject yet, so that we can apply this knowledge to the molecular systems, which would be the object of our study in the second part of the semester. Okay, so I think the first, when I write about probability theory, the first thing I should do, I should first define the probability. So where it comes from, probability. So probability comes from events which you cannot fully control. For example, if you do a coin flips, then of course mechanics says that given the initial conditions, you can calculate the outcome of your coin flip. But the problem is that if you slightly change the initial conditions, then the outcome can change. So even the slight changes in the initial conditions lead to different outcomes, and that's the reason why it's almost impossible to fully control the coin flip, given if you don't try to make some cheating. So the probability is applied to random, or there's another word, stochastic events. So essentially that means the events outcome of which you cannot control. And let's consider the coin flip. Yeah, so we have two possible outcomes, heads or tails, and we don't have any control of them. And let's say we make a coin flip for a large number of turns. So we do this continuously, and we repeat the same action again and again, and we acquire some statistics. So statistics. And we can, for example, to make this statistic numerical, we should assign some numbers to different outcomes. So let heads would be 1, tails would be 0. So if you make n coin flips, you would have an n character sequence of zeros and ones. And then you can calculate the amount of ones, the amount of zeros, and then you can divide one by another and obtain these numbers, P0 and P1, by dividing the number of outcomes by the number of attempts. So attempts of coin flip. Okay. And there is an assumption that if you repeat the coin flip for a large enough number of times, then these numbers, which are actually determined from statistics, would have some limits. So there would be a limit, okay, of this quantities P1 and P0, and these limits are called probabilities. Probabilities. Okay, so that's a kind of a statistical definition of the probability. That's not a mathematical definition in a rigorous sense, because in mathematics everything is done in a different way. There is a Kolmogorov theory of probability, and mostly all of the textbooks on probability theory, advanced textbooks, they do this in line with Kolmogorov description of probability. So they introduce some spaces, subspaces, then assign this probabilities as some functions. But the essence of this is that you want to describe these random processes, the outcomes of which you cannot control. And this can be done by these probabilities. Of course, these probabilities are slightly different from these statistical fractions, because, well, in statistics, you also have some randomness. And it may turn out that, for example, for 10 times in a row, you would have, for example, only one outcome, like heads. And then there is even a video of that. One guy has aimed to have a 10th time in a row like a heads outcome of the coin flip, and he has done this video without any kind of cutting and editing. So 10 times in a row, he had like perfectly random coin flip, and that end up in heads. But to do that, he has recorded this video for quite a large amount of time. So he had recorded, for example, I don't know how many, about 10,000 of coin flips continuously. And in those 10,000 of coin flips, there was a sequence of 10 coin flips which have ended up with heads. Heads, 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 heads. So, so there can be some deviations in the statistics from these probabilities, but these deviations turns out to be lower as you increase. You can't see the final part of the board. This one, okay, I am overlapping, so let me. Yeah, so that's from some previous.
No, it's
3 point, yes, it's 1 hour ago. Okay, so so we get the numbers which are closer and closer to those probabilities. And in the case of a good coin, these probabilities should be equal to 1 over 2, certainly. So none of the outcome is preferred with respect to other outcome. Okay, so that's the most simple example. Of course, you can have, for example, a dice. So if you throw a dice, then you have more outcomes. You may have 1, 2, 3, 4, 5, and 6, depending on which side the dice has ended up facing upwards. And of course, if we assume that the dice is not cheated, then all of these outcomes have equal probability. Of 1 over 6. And really, these outcomes are often called, how it's called, elementary outcomes. Elementary outcomes. Or events, I don't remember how it's rigorously called, but you can also construct more sophisticated outcomes. So you can try to determine the probability. For example, the probability that once you make 2 dice flips, that one of the dice has ended up as 1, while the other one has ended as 6. So that would be a more complex event than a single outcome. And probability theory allows you to determine the probability of this exact event. Okay, so far we have discussed only the so-called discrete events, so we have a limited number of outcomes, and we can assign the probability to each of those outcomes. But of course, sometimes the random numbers can be like continuous numbers. Like for example, let's say we study how people jump, and we want to determine the height or the level rise of the person upon his jump, and it's also a random number. And this random number is somewhere in between of 0 to, like, for example, 1.5 meters. And any number from in this interval can be an outcome. So that would be a continuous distribution, or it would be a continuous random value. Or, for example, if you get closer to the subject of thermodynamics, for example, the velocity or speed of some molecule is also a random value, and it's even a vector valued quantity. So, okay, if it's speed, it's a number, but it's also a random number. If you take any kind of a molecule and measure its speed, that would be a random number which has a continuous distribution. And when we have this continuous random value, or infinite amount of outcomes, then instead of the probability, it becomes more convenient to describe the probability in terms of the quantity which is called probability density. Probability density. So the probability density is the function continuous distribution. I mean a continuous random quantity. So the random quantity which can be any real value in between, for example, these two. So for example, 1.33 or 0.89975 and so on and so forth. So all of these numbers, so if your outcome can be represented by a real valued quantity in some interval, then you have a continuous random value. Yes, continuous random value. And for such continuum random value, you cannot assign probabilities in the same manner as we have done for random events which have only a finite number of outcomes, because we have infinite number of outcomes and we cannot determine the probability of each of this infinite number of outcomes, because once you have infinite number of outcomes, that means that probability of each exact number is approximately 0. So that would not give you much of an information. That would not give you much of an information. So instead of the probability assigned to each of the outcome, I need to introduce a new function which is called the probability density function. And so let's say it would be some rho of x, where x is my random quantity. So how this probability density is defined? The probability density is defined as follows. So let me plot all of these x values here. And let's say we consider an interval from x to x plus dx. Let's say x0, x0 plus x0 plus dx. So we want to find out the probability of our outcome being in this interval, small interval. And it turns out that as the width of the interval approaches 0, the probability of outcome in between x0 to x0 plus dx should be proportional to dx, and the coefficient of proportionality is called the probability density. So the probability of having your random value in between x0 to x0 plus dx is proportional to the width of this interval with the coefficient of proportionality of rho of x. Well, that's assuming that dx approaches 0. Okay, but what happens if I want to determine the probability of my random variable between some quantities a and b which are not close? For example, let's say a is somewhere here, b is somewhere here. And of course, the probability density function, if I plot this probability density function rho as a function of this x, would be some kind of a complex function, complex shaped function, not in terms like complex valued. Probability density is real valued function. So how can I determine the probability of my x value being in between a and b? The answer is as follows. I need to divide my interval from a and b into very small intervals. And of course, my probability would be sum of these probabilities, like of having x in between a plus, from a to a plus dx, plus probability of having the outcome from a plus dx to a plus 2 dx, and so on and so forth, until I reach the end. So that would give me an infinite sum of rho of x multiplied by dx. And as you know, such an infinite sum is actually integral from a to b of rho of x dx. So the probability density allows you to conveniently find the probability that that your random value appears in some interval. For example, the analog of this procedure, for example, if I apply the similar procedure to the dice, that would be like the question similar, like what is the probability of my dice having values from 1 to 4? So 1, 2, 3, and 4. So how do we calculate the probability? So we need to we need to sum up the probability of the dice having end up as 1, as 2, as 3, and as 4. So that would give me 4 over 6, which is 2 over 3. The analog of this procedure, the very same procedure for the continuous random values, is integration here, rho of x dx within the interval. Okay. Any questions about this? Because now we are starting the second part of this probability talks. So the second part is, let's say, we are going to introduce mean values. Mean, average, or expected values. Mean, average, or the mathematically correct definition is expected value. Expected value. Expected value. But in physics, all of this can be applied interchangeably, like mean speed or mean velocity or like average velocity. All of that refers to the same operation with these random quantities. So let's first define this for the discrete distribution, for the discrete random values. Let's say for dice. So let's say we throw the dice and we write a sequence of the outcomes, A1, A2, A3. So here the index is the number of my dice throwing attempt. So when I my first dice throw ends up with the quantity A1. The second dice throw gives me A2, the third A3, and so on and so forth. So ideally I can have an infinite amount of dice throws, but of course in the real case I need to stop after doing n of these experiments. So by definition, like the average value, average value, or actually it can be written like this. These are two common notations for average value of physics. It can be either these angled brackets. If you see some quantity in these angled brackets, then it means like average of some random quantity. Or if you have a quantity with this line above the quantity, then it's also the same. It applies to the average. And by definition, the average is sum from 1 to n of ai divided by the number of attempts. The number of attempts. So that's the mathematical definition of average. So this is a statistical average. But if we look at the limit of this at n approaching the infinity, then okay, we can rewrite it in the following way. So this sum contains numbers. They have 1s, 2s, 3s, 4s, and so on and so forth, up until 6. And I have n1 number of 1s plus n2 number of 2s, n3 multiplied by 3, n4 by 4, plus n5 by 5, plus n6 by 6. So these 1 to 6 are different outcomes of my dice throw, while n1, n2, n3, n4, n5, and 6 are the number of these outcomes registered during my experiment. Now again I divide by n, and as we remember the definition of the probability, n1 over 1 is the probability of having 1 as an outcome. So that would give me p1 multiplied by 1 plus p2 multiplied by 2 plus p3 multiplied by 3 plus p4 by 4, p5 by 5, p6 by 6. Or essentially this is sum of probability of having number I multiplied by this exact number I, and okay, summed up from 1 to 6. Or actually I can, this is a summation over all possible outcomes. So that's how this mean, average, or expected value works in the case of the discrete outcomes. So in the case of dice, if you have a good dice, then the mean value of, or expected value of your dice throw would be equal to 1 over 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus so on and so forth. So I need to sum up 1 plus 2 plus 3 plus 4 plus 5 plus 6 and divide this by 6 to get my average. So this is 7 over 3, 21 over 6. So this is 7 over 2. So this is 3.5. So the 3.5 is the expected value of your dice throw, which can end up from 1 to 6, but 3.5 is an average expected value. Okay. What will happen if we have a continuous distribution? Continuous distribution is more complicated. We have, instead of the probability, we have the probability density. So let's say that we have a continuous quantity, and again the same sequence A1, A2, A3, and so on of the random but continuous quantities. And we want again to determine this expected value of A. So I will start from this one. So that's what I have. I need to have the sum over all possible outcomes of probability times the outcome. But of course, I don't have the probability. I have the probability density. So that means that I need to divide all of the interval of my random quantity A into a number of into a large number of very small intervals. So instead of this sum, I would have an integral of the probability density times x times dx, and integrated over the whole real axis, or actually over the whole interval in which your continuous value can be, and divided by what? Well, I don't need to divide by anything, because rho of x times dx times n would give you the amount of the number of outcomes in which this quantity is in between x to x plus dx. So after I divide this by n, I would get the definition for the expected value, rho of x times dx. So in here I had the probability plus I multiplied by I, and summation over the whole possible outcomes. In here I have again the probability, but the probability is rho of x times dx, and again multiplied by x. So that is probably the best way to remember this equation. So this is responsible for the probability, while this is responsible for the outcome. Okay, so that's the mean quantity. Okay. Mean or average or expected value, but when you deal up with these probabilities, the mean quantity doesn't represent your all necessary properties of your random value. There is another important quantity which is called variance, and this variance describes let's say this is a characteristic value of the difference from your actual outcome and the expected value. Now let me explain this. Let's again, we have once again we have the infinite sequence of values, a1 and 3, a4, a5, and so on and so forth, and we want to determine how these values are different from your mean value. Okay, so in order to see the difference between your quantities and mean value, we construct a new sequence, a1 minus mean value of a, a2 minus mean value of a, and so on and so forth. These quantities can be negative and positive. And if I, for example, calculate the mean value, but for this new sequence, so let's say mean value of a minus mean value of a, then, okay, I apply the following property of mean values, that if I have a and b, then mean value of a plus b is sum of mean values of a and b. This is like the obvious property which comes from the definition of these quantities. So in here I have mean value of a minus mean value of a. Okay, mean value of a minus mean value of a. Since the second sequence is just a constant, so the mean value of the constant sequence is exactly it. So that means that if I calculate mean value of this new sequence, that would give me 0, so no information would be obtained from this, because it contains both positive and negative numbers. But if I, for example, calculate square of all of this, like a1 minus mean value of a squared, and a2 minus mean value of a squared, and so on and so forth, this problem would be circumvented. So I would have the sequence of positive numbers, and now I can calculate this average of a minus average a squared, and this is what is called variance. This is often described by this letter D. So this is variance, or it can be written like this, sigma a squared, where sigma a is the so-called standard deviation. Or another is root mean square deviation. all of these are like interchangeable. So variance is the square of the standard deviation or root mean square deviation. Okay, so this is this quantity. The average of the squared deviation from the mean value. This is by definition the variance. Let's do a very small exercise and determine the deviation, okay, a variance for the dice, a variation for the dice, variance for dice. Okay, we have previously determined that average value is 3.5. So now let's analyze the sequence of AI minus 3.5 squared. So let's look at the probability distribution of this function. Okay, I have P1, the probability of AI being equal to 1. So if this AI equals to 1, then AI minus average A squared is 1 minus 3.5 squared, and this is 2.5 squared. This is 6.25. 6.25. P2, the probability of AI being equal to exactly 2, then this squared deviation would be 2 minus 3.5 squared. So this is 1.5 squared. This is 2.25. And I continue this to 3 minus 3.5 squared. That would be 0.25. For the number 4, I have again 0.25, then 2.25, and then 6.25. And now I can calculate the mean value of the square deviation as follows, that D equals to 1 over 6. And now, so the probability of mean square deviation to be this is equal to 1 over 6. 1 over 6 probability of this, 1 over 6 probability of this, and of this. And I see that I have a symmetric set of values, so I can sum up only 3 of them. So this is 6.25 plus 2.25 plus 0.25 and multiplied by 2. So in the end, I would have something like 8.75 over 3. 8.75 over 3, and the 3 in the denominator is caused by the 6 and 2 after I eliminate 2. So 6 over 2 gives you 3. So in the end, I would have something which is approximately equal to 2. Okay, here goes 27, so this is 9, and here goes, okay, 2.92. So this is the variance of the dice. Okay, so there is another way to determine the variance, another equation. Let me derive you another equation. By definition, the variance is, okay, A minus A squared, and again averaged. So let's expand these brackets. So we have A squared minus 2A multiplied by mean value of A plus mean value of A squared, and again averaged. So that would give me average value of a squared minus 2 average value of a average value of a plus average value of a squared. Okay, see the difference. In here, I square up my value inside the brackets. So this is the average of the squared random value, while this is average squared. So this is the different operation, and by no means this is equal to this. This is wrong. Okay, and for here I have the product of average value by itself. So this is again average value squared. So I can continue my derivation. And in the end, I have this. Exactly the difference between squared average and average squared gives you the variance. So let's check it for this dice example. For the dice example, the possible outcomes are 1, 2, 3, 4, 5, 6, and squared outcomes are 1, 4, 9, 16, 25, and 36. So let's calculate average a squared first. Average of a is equal to 3.5. So when I do this squared, that would give me 12.25 for the average squared, while the squared average would give me 1 over 6 times, okay, here goes 1 plus 4 plus 9 plus 16 plus 25 plus 36. Well, that looks like hell amount of calculation, so it's not very convenient because the numbers are much larger than we previously had. Nonetheless, let's attempt at calculating this. I see that if I sum up 1 plus 9, I would have 10. So that's beautiful. So once again, I have 4 plus 16, which gives me 20. So the sum of the first 4 numbers would give me 30, plus 25, that would give me 55, plus 36, that would give me 91. So this is 91 over 6. If I haven't messed up anywhere, so 20, 10, 30, 55, 36, 91. So this is 91 over 6, and I don't like it for some reason. Let me see, 1 plus 2 plus 3 plus 4, because it should be divisible by 3 in my opinion. No, it should not be. So 91 over 6. Okay, that's approximately 15. Approximately 15, and 90 over 6 would give you 15, and then 1 over 6 is about, let's say 15, 17. Okay, so now I'm going to subtract to calculate the variance. I subtract squared average from the I subtract squared average from average of the squared quantity. So that would give me 15.17 minus 12.25, and that would give me 2.92. Exactly the same result as in the previous calculation. So as you see, this equation works. So if it's more convenient to you, you can calculate the the variance by this equation. Okay, so now let's slightly conclude the results which we have by far in this. I'm going to do this on this board. So the average value of A is sum of pi multiplied by I. So the probability of some event multiplied by the number associated with this event, and over the all possible outcomes. For the continuous random value, this should be modified by this, where rho of x multiplied by dx gives you the probability, and that should be integrated over the whole real axis. Next is some properties of this average. If I have average of A plus B, then I have average of A plus average of B, where if my A and B are random quantities. But if I have, for example, my random quantity multiplied by some constant, not random quantity, just constant, then I can take out the constant from the average. But for example, if I have the average of the product of the two random values, then not necessarily this is equal to the product of averages. Sometimes it is, but often it is not. And one of the examples is that A squared average is not equal to A average squared. And even I have the definition of the variance. Okay, let me write the variance in here. The variance is by definition an average of the squared deviation from average. Or alternatively, the difference between average, okay, squared average minus average squared, like this. So these are the properties. Now I should also write for the definition for the variance for the continuous values, but as you see, it mostly my variance is defined through averages, and I have the definition for average. That's why I can write for my variance the following expression, that this is the integral of rho of x, okay, for example, of x squared minus average x squared over dx. Very good. Okay, and let's now touch another important property of the probability. This is called the normalization property. Like if you have some attempted, acquired some random quantity or random outcome, the probabilities of independent random outcomes should sum up and give you 1. Otherwise, you don't have a complete set of variables. For example, if you have a coin, then the probability of 0 outcome and 1 outcome should be 1. If it's not 1, then it means that there are some other possible outcomes which have not been accounted. For example, let's say if I do coin flips, I may be interested in the probability of the dinosaur catching my coin and eating it. So this is a very they fail in acquiring the result. So if I include this probability that for some reason I might not get either 0 or 1, but nonetheless with these events all of them should sum up and give you 1. Or, for example, if I throw a coin and after it falls down, it remains on the edge, not flipping onto one or other side. So it's perfectly on the edge. So like plus probability of edge. Yes, this is almost improbable event, but sometimes that may happen. But all in all, if you sum up the probabilities of all possible outcomes, they should sum up and give you 1. Because, well, I think that follows from the definition. So if you have n number of experiments and you have recorded number of outcomes n1, n0, and other, so the total number of experiments should be sum up of the number of different outcomes you consider in your problem. And if you divide all of this by n, that would give you 1 is equal to p1 plus p0 plus everything else. So this is called normalization condition. Normalization. And if you work with the continuous values, then your normalization should be modified. Then normalization looks like this. So instead of the sum of all of the probabilities of all different outcomes, you replace the probability with the probability density multiplied by dx, and instead of sum, you have integration. Like here, I have replaced the probability by rho of x multiplied by dx, and replaced summation with integration and obtain the analog of the expression for the continuous values. In this case, the normalization is again obtained from sum of the probabilities by replacing the probabilities by rho of x dx and replacing sum by the integral. It can be considered a general finger rule for calculating some quantities for continuous distributions. Okay, the next part of this lecture would be about independent and independent events. Okay, in this part of the lecture, I'm going to discuss the independent quantities or variables. And probably the first theorem which should be proven for independent events is as follows. If A, so this is a theorem, if A and B are independent events, then the probability of combined event AB, which means like A has happened and B has happened, is equal to the product of probabilities of each events. So it's like this. P of AB equals PA times PB. I don't have a proof for this, but I have, it's probably one, is the postulated in probability theory, but I can give an explanation for this. So A can be event. Let's say A, it can be a complex event like in the dice roll, you have an outcome of 1, 3, or 5. You have like odd outcome, odd number as an outcome. And B can be also in a dice roll, you have an outcome of 2, 4, or 6. So you have even number. And this combined event AB means like in one row you have outcome A, in another row you have outcome B. So, like for example, consider two rows, and of course, in each row, the result of the next row is independent of all of the other rows. In each of the row, the number which you get is perfectly random. It's independent of your previous results. So I can make this combined event. Like for example, in the first row, I have odd number. In the second row, I have even number, for example. So how can I explain this? I can do this like geometrically. Why this is the probability is equal to the product. So let's say that when the result of the first event is being determined, I can do it like follows. I have a line, and I chose a point randomly on this line. And if my point is in this region, then I say that event A has occurred. But if my point is out of this region, I say that event which is called not A has occurred. So for example, if I have chosen A to be the dice roll giving you odd number, then event not A is the dice roll giving you not an odd number, or actually the even number. And the same I can do with this event B. So if I chose the random point. If I have the point in this interval, then event B has happened. But if my random point is out of this region, then my B hasn't happened. And of course, if I can choose any point of this interval at random, the probability of the event A is actually the ratio of lengths, the length of this part of the line to the total length of the line. And for the B, probability of the event B is given by the ratio of the length of this interval, which represents your event B, over the total length of the line L. So, this is the geometrical representation of probabilities. I would say so. So you can put into correspondence. So your random events can be put into correspondence with this random choice of the point on the line. So when I have these combined events, I need to choose one random point on this line and one random point on this line. So altogether, this is exactly the same as choosing a random point in this square. So when I choose two random points, so I choose actually random point in this square. And this region of the square corresponds to the event AB, which I'm so interested in. This corresponds to not A and B, this corresponds to not A, not B, and this event corresponds to A and not B. And as you see, if you randomly choose the point inside this square, the probability that you actually choose the point inside this part of the square is equal to the ratio of the area of the region AB to the, okay, let S be the area, to the total area of my square. And of course I can write that this is actually equal to LA times LB over L squared, and this is equal to the to the product of probabilities P of A times P of B. So that is how it works, that if I have two of these events, and these events are independent, so the result of the second attempt is independent of the previous history, and then I would have the probability of the combined event to be the product of the probabilities of initial events. Actually, the independence of the result of your random throw on the previous results is slightly counterintuitive. For example, let's say if you are tossing a coin, let's say you have obtained heads in your toss, then you would expect that for the next toss it is more probable to have the tails, but it's actually not. The probability doesn't change. In the next toss, you have exactly 50% probability of having heads and 50% of probability of having tails. So if you have heads as the first throw, then these two possible outcomes after the second throw have exactly the same probability. They have exactly the same probability. And now let's move from discrete events to probability distribution functions. Let's say we have two random quantities, continuous random quantities x and y, and I can generalize the concept of the probability density to describe the joint distribution of these quantities x and y. So I can say that the probability of x being between x0 to x0 plus dx and y being between y0 to y0 plus dy is equal to the density of x0 and y0, probability density at the point x0, y0, multiplied by dx dy. And of course, I mean by this equality, I mean that this is the limit at dx dy approaching 0. So if I have sufficiently small intervals, dx and dy, so that's how I get this probability. And as you see, if my x and y, if x and y are independent, then in the condition of the previous theorem, I can write that actually this probability, this combined probability of x being in one interval and y being in another interval is the product of these probabilities, x from x0 plus dx multiplied by the probability of y0 to y0 plus dy. And that gives me, from this expression, and then changing these probabilities, expressing these probabilities through probability densities, I get that my joint probability density rho of x0, y0 should be equal to the probability density of x at x0 multiplied by the probability density of y at y0. So this is valid for independent variables. But if those variables actually depend on each other, like for example, this quantity y is somewhat determined by this quantity x, then of course this is not valid. And this is often used as the criteria for the independence of quantities. So if you have this, then you can say that these quantities are independent or uncorrelated, or actually not correlated. So x and y are not correlated. Well, of course, in the events, it's very difficult. Well, in reality, it's very difficult to measure these probability densities. What you can actually measure, you can measure some averages or deviations like variances. So I need to write this criteria for the independence of two different quantities in terms like of average. So I can do this. Let's consider the average of xy, the average of these two quantities. By definition, this average is equal to the probability density at xy multiplied by xy and integrated over dx dy. Then using that equation on the right part of the blackboard, that the joint probability density is given by the product of individual probability densities, I can write that this is rho x of x multiplied by rho y of y multiplied by xy dx dy, and then it can be presented as the product of two integrals. As you see, and each of these integrals, yes, so I used this to convert from this to this, and then according to the common rules for multiple integrals, I can present this as the product of these two integrals, and each of these integrals is average of x and average of y. So as you see, for independent variables, for independent random variables, I can write this. xy equals to the product of averages of x and y. And of course, if I have variables x and x, which are dependent on each other, then of course the average of x squared, which is average of xx, is not equal to average of x multiplied by average of x, which means average x squared. So this really applies only to independent variables. But if the variables are not independent, then we can measure a so-called correlation function. The correlation function is exactly this difference. So it can be positive, it can be negative, but well, if this quantity is not zero, that means that these two variables are somehow connected to each other. They are not independent. And oftentimes, like for example, if you hear news, like mostly in medicine and biology and sociology, they're interested in some correlations. And sometimes it is one of the lines of research in which you seek correlations in between seemingly uncorrelated values. Like for example, you try to find the correlations between the age and and wealth, yeah. So you find the correlations, or like you find the correlations between your love to chocolate, yes, to chocolate, and the heart disease. Yeah, so people, they study, they have a large sample, so they have a large number of people who they study, and they ask them whether they love the chocolate or not and how much. So they want people to grade their love to chocolate, and then also look at the medical analysis and look at the shape of their heart, and like for example, ask them whether they had some seizures, and then find the correlations between these two. And one of the famous results is the correlation between the cholesterol in your blood and also the amount of therms in your vessels. So this one actually turned out that the more cholesterol you have in your blood, the more you are susceptible to having therms in your veins. But the problem is that if you have, like, for example, two correlated values, it doesn't mean that one value actually affects another one. So there is a very important rule that correlation does not mean causation. So if you, like, for example, observe some correlation between these two, it might not be as if one quantity is influenced by another. Like, for example, on this correlation between the cholesterol in blood and like your overall vessel health, well, it was suggested to improve the health of people by reducing the amount of cholesterol in blood by administering people drugs which decrease the concentration of cholesterol in blood. But it turned out that actually the therapy doesn't help too much, unexpectedly, because these two numbers are being correlated because, like, for example, like, they have the common cause for the increase. Like, for example, some violations in your diet or some deficiencies in your daily routine lead you to accumulate more cholesterol in blood and lead you to worse health in terms of your vessels. So, but actually affecting this one by medicaments doesn't lead you to improvement of this, because if this reason is not eliminated, you would not have a health improvement. So actually, well, by now, like, the most important part of your therapy, like, you need to move more and you need to have a healthy diet in order to improve your health. So that's because this is the reason behind the health malfunctions. And yeah, so if you have some kind of a correlation between two quantities, it doesn't actually mean that these two quantities are connected by the cause and consequence relationship. Another example is in the economy. Well, I am not a specialist in economy, but there was a theory in which like related the economic growth and as far as I remember, the how it's called, like the main percentile of central bank. And as you know, there is this this percent for the overnight loans from the central bank, and this percent actually quite determines you how much the money costs in your system. And it was determined probably in 60s that for the economies which had this percent in between 2 to 4%, they had the highest rate of growth. But when governments wanted to improve the economical state, or wanted to increase the economic growth by changing this this percentile of central bank, this law immediately crumbled, because, for example, these two stuff, like economic growth and this, they are connected by some reasons, by the same origin of the economic growth, which doesn't require you to have a very high rate of interest in your central bank. But nonetheless, if you want to affect one parameter by changing another, it doesn't happen. So because this is not directly related to the economic growth. Okay, so so correlation means that your quantities are related to each other, but that doesn't mean that actually one quantity is determined by another quantity fully. Good. And okay, the next part, what I wanted to say else. Okay, this is for independent. Okay. The next one is a so-called central limit theorem, which is very important. Limit theorem. It says that for example, if you have multiple independent random values, x1, x2, x3, and so on to xn, if you create a new random variable by summing up all of these random variables, then we can say something about the probability distribution of this number. Theorem says that x would be normally distributed if the number of random variables which compose this capital X approaches the infinity. Now I should explain what normally distributed means. Okay, normal distribution is the type of the probability distribution which has the following formula. Let me give you this equation. Okay, normal distribution. One over square root 2 pi sigma. Okay. Sigma is not in the square root, multiplied by exponent of minus 1 over 2 x minus mu squared over sigma. Okay, so this is the exponential distribution function. If you plot the dependence on this function on x, that would give you a bell-like shape function, symmetric bell-like shape with the rapidly decaying tails, and the peak of this function would be at x equal to mu. And actually, this mu is mean value of x, while sigma, while the variance of this distribution is equal to sigma squared, and sigma is again standard deviation. So this is called the normal distribution, and central limit theorem says that if you have multiple independent quantities which can have any kind of a probability distribution, then in the end, if you sum up all of them, you would have a normally distributed quantity. And moreover, let's consider a variance like of a sum of over some of these quantities. So let's say that I have a quantity x which has some expectation value or mean value of mean x, and which has some variance of dx. So let's determine and now we have another quantity y, which has again this mean and variance, and let's determine mean and variance of x plus y. Okay, for the mean quantity, the calculation is very simple. This is mean of x plus mean of y. That follows from the properties of mean quantities. But if I want to calculate the variance, what should happen? So in here, variance is like x plus y squared minus mean value of x plus y squared, this average. And after I open all of these brackets, so I have mean of x squared plus 2xy plus y squared minus this minus this minus this, and all of this under the averaging function. So, and now I should open all of these brackets, and I would have this. And as you see, these two are mutually eliminated. Okay, this is 2. So I have here this plus minus this plus the same for y. Which is actually the sum of variances for x and y. So as you see, not only if I have independent, that's what's important here, independent. If I have independent quantities, then the mean quantity of the sum would be a sum of means, and the variance for the sum would be sum of variances of individual numbers. And if I have a huge amount of them, then that would give me like the average of capital X, and let's say actually all of these quantities are exactly the same quantity but measured at a different outcome. So let's say if I have multiple experiments repeating, for example, dice roll or measuring some kind of a random quantity, so all of these have the same mean and the same variance, then mean of the capital X quantity would be equal to n times the mean of a single quantity, while the variance of the capital X quantity is again n times the variance of small x quantity. And what's importantly in here, so as you see, I need to multiply all of them by n. But if I calculate the standard deviation of the capital X, that would be square root of n times the standard deviation of the small x. And if I calculate relative standard deviation of the capital X to the, so that would be 1 over square root of n times the relative standard deviation for a small x. So as you increase the number of terms, this new probability distribution would be more and more centered around the average value. So let's say, for example, if I consider not the sum of these quantities, but for example, I take y, which is determined as 1 over n times x1 plus x2 plus so on and so forth, plus xn, then for this quantity, I would have average of y to be equal to average of x, while the variance of y would be equal to 1 over n multiplied by variance of x. Because by the definition of variance, if I divide all of my quantities by n, then my variance would be divided by n squared. So that means that if I do this averaging, then the probability distribution function for this average would be much more centered. So if I, for example, have a quantity which has this kind of probability distribution, rho of x, but if I sum up n of these quantities, a very large number of these quantities, And then the probability distribution of the result would be something like this. And here, if I have the 0 and 1, that would be centered around 1/2. So this is actually one of the reasons why thermodynamics can work, because you have a very large number of atoms and molecules, and when you average some characteristics over the atoms and molecules, for example, if you look at the average kinetic energy of the single molecule, so this is a quantity which is pretty well defined here. So as if you have n around 10 to the 23, so if you look at this, then you should divide the variance of a single molecule by 10 to the 23 to get the variance in the average kinetic energy per single molecule. Well, that means that essentially this quantity is well established and it doesn't fluctuate. Okay, I think we will continue this on the next lectures, but please remember that the central limit theorem plays a very important role in thermodynamics, and it plays a very important role in all of the applications of statistics and probability theory. And one of them is that it allows to introduce thermodynamic variables. Thank you for your attention. See you next time.